How's everybody doing? Welcome back to Math for Healthcare video lecture series. Um, Here we're starting a new unit, Unit 4. Now, we saw, so this obviously from my title here, right? Introduction to Counting. Counting seems like it should be easy. It's not that easy. But we're going to learn some basics of it. And when I say counting, I mean counting the arrangements of things. For instance, stuff like if I'm tossing a coin 10 times, how many ways is there to, what's the size of my sample space? And if I wanted to find the probability of getting two heads and I'm tossing a coin 10 times, I'm going to have to count the number of ways to get two heads if I'm tossing 10 coins. So we're really going to use this in order to be able to find probabilities and understand probabilities. All right? So the first thing we learn, well, I basically just said that this one, is what's called the multiplication principle. Okay? And here, our example is a sandwich shop has 4 kinds of meats and 3 kinds of cheeses. Each sandwich can have 1 meat, 1 cheese. How many different types of sandwiches there are? So let's think about this. Oops, went a little too far. This is actually basically a tree diagram. What do we have? We have 4 different kinds of meats. So that's 4 branches right off the bat. I don't know, let's say salami, turkey, just a little more condensed. What else we got? Pastrami and ham. Okay. Now we have to, once we pick those for each of those meats, then we have 3 choices for our cheese. Okay, so let's say cheddar, Swiss, and pepper jack. Right? There's going to be one each of these. Swiss, pepper jack. Cheddar, Swiss, pepper jack. Cheddar, Swiss, pepper jack. Now, just like before, is we want to count what are all the possible sandwiches? It's all the possible paths. Like that path, right, includes that path includes salami and cheese sandwich. Okay, so how many are there? Well, there's 4 original ones, and then for each of those 4, there's 3 choices, and so that's going to be 4 times 3, which is 12. And notice here is if we count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's our multiplication principle. And stated in all its glory is saying, suppose there are m ways of performing task 1. So we have m, m branches at first. And then task 2 would be like our cheese. We have n tasks for that. And how do we make them? We multiply the 2. Okay, and that's called a multiplication principle. And that's basically when you could say, for each one of these, there's this many others. And notice it also goes with intersection, just like what was down the whole path, we multiplied down it. It's the same idea. Okay, so how about this? A restaurant has 5 different entrees, 6 different side dishes. How many ways are there to select a meal consisting of an entree and a side dish? Well, using a multiplication rule, task 1 has 5 different ways. Task 2 has 6, and that gives us 30 possible meals. of entree and a side dish. How about if we have Mr. Potato Head? He has 3 hats, 5 mustaches, and 4 kinds of glasses. How many ways are there to dress him up? This is just like this is the multiplication principle, except for now we have 3 tasks. So you can imagine there's 3 sets of branches on your tree diagram. It gets messy. I'm not going to draw it, but let's see. There's 3 ways to choose the hats, times 5 ways to choose the mustaches, right? And that's, again, for each of those 3 hats, there's 5 different ways to choose the mustaches. Now, for each of these 15 ways that there's to choose the hat and mustache, there's another 4 ways to choose the glasses, and that gives us 60 possible ways. And this is an example of the generalized multiplication principle. We have n choices being made with m1 ways to make choice 1, m2 ways to make choice 2. Another way to think about that is, and then we multiply them all together. I would say something like this. I have, let's see, this is task 1, task 2, task 3, task 4, task 4, task 5, and it would be m1 ways to do task 1, m2 ways to do task 2, m3 ways to do task 3, 4 ways to task 2, m4 ways to do task 4, and m5 ways to do task 5, just like with Mr. Potato Head, and we just multiplied those all together. Okay. 6 different character license plates are there, where the first 3 characters are letters and the second 3 are numbers. Now, I really like having, when I'm doing counting problems, a lot of times as I write down dashes to mean things. Here, we have 6 characters to fill in. And these 2 are both letters. Oh no. Sorry. This is saying these 3 are all letters, and these 3 are numbers. When we say numbers, we mean digits, and the digits are from 0 to 9. All right? And then we figure out, okay, what is that? We got, 26 ways to choose the first letter or do task 1, 26 ways to choose the second letter, because there's 26 letters in the alphabet, 26 letters to choose the third. Now, how about digits? Digits are 0 to 9, so there's 10 ways to choose the first digit, 10 ways to choose the second, 10 ways to choose the third, and you get 26 cubed times 10 to the third. And I'm okay with solutions like that, but please feel free to use Desmos to calculate things. I thought I erased. Oops. Okay, so bike lock requires 4 digits, 0 to 9, to be selected in order. How many different combinations are there? Well, again, now I got 4 different digits. There's 10 ways to choose the first, 10 ways to choose the second, 10 to third, 10 to fourth, and we get 10 to the fourth ways, which is what, 10,000? Now, how many 4-digit college extensions are there if the first digit can't be a 1 or a 0? Well, similarly, we got 4 digits we're choosing. But now the first one can't be a 1 or a 0, so there's really only 8 ways to choose the first digit, and 10 to choose each of the third 3, and that gives me 8,000, or 8 times 10 to the third. Right. Now, let's think about, so what is the size of the sample space if we're tossing a coin 10 times? Well, here we have 10 dashes. Sometimes I don't want to write them all. And what? What are the how many ways? Oh, there's 2 ways for the first coin to call, 2 ways for the second coin, 2 ways for the third, well, all the way through 2 ways for the 10th. So we're doing 2 times 2 times 2 times 2, 10 times, or 2 to the 10th to find this when we're tossing coin 10 times. Now, when you're doing these problems, it's one of the ways to do them is to identify the archetype. And what I mean by that is here, I asked, what's the sample space of tossing a coin 10 times? There's 2 to the 10th. If I asked how many strings of zeros and ones of length 10 are there, there's the same thing, 2 to the 10th, because you have 2 for each one. Right? And that's seeing the similarities between those two things. Okay, so what is the sample size of space? How about if we roll 5 die, right? Well, now we have 5 slots, and there's 6 possibilities for each, so we're going to get 6 to the 5th. All right. So I want you to go ahead and hit pause and try these on your own. All right, I'm going to go through and say 1. Okay, 5 flights, 8 different hotels, 7 rental cars, 5 times 8 times 7. I'll let you double check whether you got that correct or not. Combination requires 3 numbers from 0 to 39. So now this is more of a spinner. It's not digits. But you can't have the same number twice in a row. How many different combinations are possible? This is a little trickier. And this here is, there are, 0 to 39, that's 40 to choose the first thing. But we can't have the same number. Now, for the second one, there's only 39 because we can't have whatever that first number was. Third number is not 38, but 39 again because it just can't be the middle number because it's in a row. So we get 40 times 39 squared, and I'll let you calculate that. Now, this is kind of similar. We have a teacher has 5 different books that she wishes to arrange side by side. How many different possible arrangements are there? Well, let's see. Think of them in a line. We got 5 books. Okay. Well, how many ways can I choose the first book? There's 5. How many ways to choose the fourth book or the second book? Well, now there's 4 books left, so you only have 4 choices. 3 and 2 and 1, so we get 5 times 4 times 3 times 2, 1. And this is new notation now. We call this 5 factorial. Okay. And what is that? 20 times 6, this is 60. In general, that factorial notation is n factorial equals n times 1 times n times 2, all the way down to 1. By definition, sort of, I'm not going to take the time to explain it, but 0 factorial equals 1. All right. So, that we could think of that as what's n factorial? It's the number of ways to arrange n distinct items, whatever that may be. Okay? How many ways can I arrange the numbers from 1 to 11? Is going to be 11 factorial. Right? Same thing. Same as the books. Anytime I have that arrangement. Now, suppose that a teacher in the last slide was to place only 3 of the 5 books. How many arrangements of these 3 books are possible? Well, we have 5 for the first, 4 for the second, and 3 for the third, and we get 5 times 4 times 3, and that is going to be 20 times. Oops, did I miscount the last one? Yeah, the last one must have 5 factorial is 120. Sorry, 5 times 4 times 3 is our 60, and we also have a special way with this. It's called the permutation of 5 things taken 3 at a time. Okay, this is the formula for these things. We don't really care about the formula too much, and I will remind you that you could find this in Desmos, and it's going to be NPR. You could type it in, or you could find it under the stats stuff. And for instance, 5, 3 is equal to permutations of 5 things taken 3 at a time. Okay, so the permutations thus far that we've considered have all distinct objects. Notice they've all been distinct. In many situations, we're interested in finding the number of permutations of a set of objects, which not all objects are distinct. So something like rearrange the letters of the word tatter. Well, here, if they were distinct, think to yourself, how many would there be? 6 factorial, right? However, for each of those arrangements, we have, if we're not considering the t's distinct, we got to divide out by that, and that's going to be, here we have 3 t's that are repeats, so you divide by 3 factorial. This is 6 times 5 times 4. Again, this gives me 120. Okay, good. So Mississippi, how can that be arranged? Now we have more than one repetitiveness, but we have a total of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial divided by. So let's see here, we got 4 s's. That gives me a 4 factorial on the bottom. And we got 4 i's. That's another 4 factorial, multiplying those two. And then we have 2 p's, so 2 factorial. And I'll let you put that in your calculator, find the number of ways. But that's with repetition. Now, how about a student buys 3 cherry yogurts, 2 raspberry yogurts, and 2 blackberry yogurts. She puts them in the dormitory fridge to eat 1 a day for the next week. How many ways can she select yogurts to eat for the week? Okay, so this seems like different than the Mississippi problem, but it's really the same. Because really what you're asking for is how many arrangements of, say, C, 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 R, R, B, B. And hopefully we see how that connection, so we get, let's see here, 7 factorial divided by 3 factorial times 2 factorial times 2 factorial. All right? So that's permutations with repetition. Or, sorry, permutations with where you have non-distinct items, right? Here. And I really want you to pay attention to this, going from 3 cherry yogurts, 2 raspberry yogurts, and 2 blackberry yogurts to deciding that that's the same as asking how many arrangements are there of these letters. That's an important task. Okay. We're going to stop there. And then next time we're going to look at combinations, which is the kind of partner to permutations that doesn't have ordering involved. For instance, how many ways are there to choose 5 things from a bag where the order doesn't matter? Or how many ways are there to choose a committee of 5 from the United States Senate? Yeah, so go ahead and practice a couple problems. You won't be able to do all the problems in the next homework, but you should get started, and the next video will be up soon.